I made an allusion to before, there is a better way to calculate a change in enthalpy than by using bond energies. And the reason for that is that bond energies don't take into account what phase a substance is in, whether it's a solid, a liquid, or a gas. And that phase is important because there are different energies that are possessed depending on the phase of the substance. Now, enthalpy is considered a state function, and here's what that means. Again, I'm going to kind of refer back to the physical science class that I'm assuming that you probably had maybe as a 7th or 8th grader or even as a freshman. If you talk about calculating the potential energy, say, of a box, and if you have a box sitting at one level and then you raise the box up to a higher level, then the box has more potential energy at the higher level than it does at the lower level. Hopefully that's something that you remember. Well, it doesn't matter how I get the box from here to here. It doesn't matter if I shove it up a ramp, if I rig up a pulley system and lift it up that way, if I just lift the box from a lower level to a higher level. Once I get the box up to this higher level, it's going to have the same amount of potential energy regardless of how I got it there. Enthalpy works the same way. It doesn't matter how you get there as long as you've gotten there somehow. And so any type of a state function basically says that it is independent of path. And I did link you to another video where a gentleman does a really good job of explaining what a state function is all about. So I want to make sure that you watch that and pay attention to that. What I'm going to do now, though, is I'm going to show you how to calculate a change in enthalpy for a reaction where I'm not using bond energies, but rather I'm using enthalpies of formation. Well, what does that mean? The enthalpy of formation means that how much change in enthalpy was there, how much potential energy was there based on the formation of that compound. Again, it doesn't matter how I got there, just the fact that it was formed. And so the symbolism that you're going to see is the H for the enthalpy, and you'll see a little subscript F, which means formation. And then you'll see a degree sign up here. And what that means is that the degree sign means that it was at a specific temperature in order to calculate what this is. If the temperature changes, the enthalpy of formation changes. And so everything that we're doing is at a standard temperature, which is going to be room temperature. Okay, it's going to be, I believe it's 25 degrees Celsius. So that is enthalpy of formation. And again, there are charts in your book where you can find standard enthalpies of formation for a variety of different compounds. And we're going to use something called Hess's law to determine the change in enthalpy for a reaction. Now, hopefully I didn't confuse you in the first video, because I think I had written on the board potential energy of the products minus the potential energy of the reactants. And then when I went down and I did that sample problem for you, I actually did the reactants minus the products. This is the one place where you're going to have to be careful in working these problems, because when you work problems with bond energy, you're going to take the products and you're going to subtract that from the reactants when you use bond energy. So there, it's reactants minus products. But everything else that you do in this chapter now, you're going to be taking products and subtracting reactants, okay? So just keep in mind that when you work the bond energy problem, you do this subtraction in the opposite order that you're going to do everything else that we're going to be doing from here on out in this chapter. So I gave you a sample problem. If you have that sheet pulled up, the sample problem says some gasoline companies put a small amount of liquid ethyl alcohol, or it's also called ethanol, into their gasoline. What is the delta H for the complete combustion of this chemical? Well, the first thing I need to do is figure out what the complete combustion reaction is going to be. And the problem tells us that the formula for ethanol is C2H6O. and that is in liquid form, okay? You probably do hear an awful lot, if you're in the States very often at least, you hear a lot about ethanol. Ethanol is made from corn, and ethanol is very often added to gasoline. Now, when something combusts, what does that mean? Well, hopefully you remember from our chapters before that means we're going to react it with oxygen, and we are going to assume a complete combustion, which means what are our products going to be? You're going to have carbon dioxide, and you're going to have water vapor if you have complete combustion. Okay, so then we need to balance this equation. You'll notice I have 2 carbons here, so I'll need to have 2 carbons over here. I have 6 hydrogens on this side, so I'm going to put a 3 in front of the water so that I have 6 hydrogens on this side. Number of oxygens on this side, I have 4 here and I have 3 here, which makes a total of 7. I have 1 in the ethanol, and so if I put a 3 here, that'll give me 6 plus this 1 will make 7 on this side. So first of all, in order to work these problems, you have to have a balanced equation, so that's always your first step. And depending on what the reaction is in some of the problems that you're going to be working, they may already give you a balanced equation. So you may be able to skip this step depending on the problem that you're working. Okay, so the next thing that you have to do is you have to have that table of standard enthalpies of formation in front of you in order to pull these numbers off. So the delta H for the reaction at standard temperature, and so I could put that little degree sign up there. I'm going to start with the products. So I have 2 moles of carbon dioxide, and so if you look at the table, you will see that the standard enthalpy of formation for that is a negative 393.5 kilojoules per mole, and I'm going to multiply that by 2 moles because there's a 2 in front of my carbon dioxide. Okay, then I've got water vapor. When you look at the table for this one, make sure you get the gas. You have to make sure that you get the right one. Don't get the liquid, because in this reaction, this is in the gaseous state. So I have 3 moles of that because there's a 3 in front of there. And then that is a negative 241.8 kilojoules per mole. And so you'll see what we're doing here is very similar to what we did in the bond energies. Your moles are going to cancel out, and you're going to be left with kilojoules, which is the unit of heat for the enthalpy that we're going to be calculating. So these are the products. On the product side of the reaction, we need to subtract the reactants. So the liquid ethanol, I have 1 mole of that, and the enthalpy for that is a negative 277.7 kilojoules per mole. And then I've got to subtract off the oxygen. Now, if you have a compound, or in this case it's an element, if you have an element, a compound wouldn't work. If you have an element that is at room temperature in its natural state, and oxygen is normally a gas at room temperature, we know that because we breathe it all the time, and so since this is in its natural state at room temperature, the delta H of formation for this is going to be 0. So I'm going to take 3 moles, but really what I'm doing is I'm multiplying it by 0 because this is an element in its natural state at room temperature. Okay? Be careful with your signs. Make sure that you start off, everything on the product side needs to be added, and then when you subtract the things on the reactant side, make sure that you're subtracting both of those off. So again, as you're typing all this into your calculator, be very, very careful to make sure that you're hitting negative numbers when you're supposed to be hitting them. Make sure you're hitting minus signs when you're supposed to be hitting them, so that you end up with the correct sign at the end. So let's stop and think here for just a second. If this is a combustion reaction, combustion reactions give off energy, yes? Combustion reactions give off a lot of heat. So what should the sign on my delta H be? It's exothermic. It should be a negative number. And if you type all this in, what you should end up with is you're going to have a delta H of a negative 1234.7 kilojoules. You'll see that it is negative, and so therefore this reaction is exothermic, just as we predicted it would be because it is a combustion reaction. So you are going to be doing a lot of samples of these types of problems where you will be using the table with the enthalpies of formation. Don't forget that if it's in its natural state at room temperature, then this is going to be 0, and so don't let that confuse you there.